Hello guys, welcome to my channel. Today we have a beautiful math problem that was first solved by a French lawyer, François Viète. François Viète, who is also titled as the father of modern algebra, was a lawyer by profession, but he was also serving for King Henry III and Henry IV in France. And he was actually working as a code breaker during wartime, and when he broke the code of the Spanish, he was accused of being a witch too. So he was a lawyer, he was a mathematician, he was a politician, and he was a witch. Let's get started with this beautiful math problem today. Okay, let's get started. This may seem a little bit monstrous at first and impossible to crack, but by identifying some patterns, we might be able to solve this problem actually very easily. What I see is that I have square root of 2 in almost every nested term here. So I may be able to extract those square roots of 2. And the second pattern that I see is square root of 2 over 2 reminds me of cosine of pi over 4. So let's do it this way. Let's have this at hand and try to extract every square root of 2 over 2 from the second, third, and all the subsequent terms. So I'm going to write square root of 2 over 2 dot extract 2 and write 1 plus square root of 2 over 2 and over 2. This is actually 1 plus the first term, right? So if I find the first term, which is cosine of pi over 4, I can replace the square root of 2 over 2 in the second term. And in the third term, I'm going to do exactly the same. I'm going to extract 2 and then write 1 plus square root of 2 plus square root of 2 over 2, parentheses closed, over 2. And then this continues on and on. And what you can see is that here, let me try to highlight it. Here, this is actually the second term. This one is the second term that we had here. So I can replace this one with the second term that I'm going to find later. Okay, so instead of square root of 2 over 2, I'm going to write, excuse me, let me change it to a pen. And let's continue in red. So I'm going to write cosine of pi over 4 dot square root of 2 times 1 plus cosine of pi over 4 over 4. I brought 2 inside the radical, so I wrote 4 instead of 2, right? So, and the third term, I'm going to keep it the way it is for now. 1 plus square root of 2 plus square root of 2 over 2 and bring 4 inside for now. Okay, so we have an identity, a beautiful identity, and that is cosine squared of theta over 2 is equal to 1 plus cosine of theta over 2. So this is another beautiful identity we can use here. So this is going to turn into cosine of pi over 4 dot square root of 2 and 4 are going to cancel each other out. So it's going to be over 2, 1 plus cosine of pi over 4. So if theta is pi over 4, 1 plus cosine of theta is going to be 2 times, this is going to be brought here, 2 times cosine squared of theta over 2, right? So I'm going to write it this way. 2 times cosine square of theta over 2, pi over 4 over 2 is going to be pi over 8 dot third term, I'm going to write it this way. Okay, so let's scroll up and scroll down. Yeah, so okay, so cosine of pi over 4 dot 2 and 2 cancel each other out. Cosine squared of pi over 8 is going to turn out to be cosine of pi over 8. Now in the third term, what's going to happen is I have 2 in the denominator, and we know that this is the second term, right? So this is going to be 1 plus cosine of pi over 8. And I'm going to replace 1 plus cosine of pi over 8 with 2 times cosine squared of pi over 16. And 2 and 2 are going to cancel each other out. So this is going to be equal to, and a lot of dots here, cosine of pi over 4 dot cosine of pi over 8 dot cosine of pi over 16, and this continues on and on to the infinity. Okay, so this is what we are going to deal with now. Okay, so here we're going to use another beautiful identity. Cosine of, sine of 2, let's say alpha, is equal to 2 times sine of alpha dot cosine of alpha. If I rearrange, this is the third identity we're using here. If I rearrange, cosine of alpha is going to be sine of 2 times alpha over 2 times sine of alpha. So I'm going to replace every term in this series with what I have here. So cosine of pi over 4 is going to be sine of 2 times pi over 4 sine of pi over 2 over 2 sine pi over 4. That cosine of pi over 8 is going to turn out to be sine of 2 times pi over 8 pi over 4 over 2 times sine of pi over 8. Cosine of pi over 16, sine of pi over 8, 2 times sine of pi over 16, right? And this continues on and on again. So, okay. Now, let's see. This is a telescopic product, by which I mean this is going to cancel this term, this one is going to cancel this term, and this continues for like ever. So let's continue in another color. So what I have is sine of pi over 2, 2 to the power of n, because there are n 2's here, right? 2 is 2 to the power of n, then sine of pi over 2 to the power of n plus 1. Sine of pi over 2 over 2 to the power of n, sine of pi over 2 to the power of n plus 1. So this is indeed the series that we're trying to find the result of, and n goes to infinity here, right? So let's rewrite this. Sine of pi over 2 is equal to 1 over 2 to the power of n sine of pi over 2 to the power of n plus 1. And the thing is, sine of x, when x goes to infinity, is equal to x. So here we can write that 1 over 2 to the power of n sine of pi over 2 to the power of n plus 1 is going to be pi over 2 to the power of n plus 1. And this is going to be, these two are canceling each other out, is going to be 1 over pi over 2 or 2 over pi. This is lovely, isn't it? Like pi turned out in a very, very unlikely place. I didn't expect it to happen here, but it turns out to be 2 over pi. So scrolling up, oopsies. Okay, scrolling up, this is going to be equal to 2 over pi. Please subscribe to my channel and drop a comment and like my video. Thank you.